The distance across the universe is not a number. It is a lie. You were taught the observable universe spans 93 billion light-years wide, and you probably assumed that meant you could draw a line from here to the farthest visible point and call it a journey. You cannot. At the largest scales of the cosmos, distance itself stops working the way your brain expects. Looking farther across the universe does not just mean looking at something more remote. It means looking backward in time, seeing ancient objects that may no longer exist in any form you would recognize, sitting in places you could never visit, even if you traveled forever at the speed of light. The universe can show you things it will never let you reach. If you find these kinds of deep explorations about the universe fascinating, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. You have been measuring things your entire life. Height, weight, the distance to the nearest store. Measurement is how humans make sense of the world. Something unknown becomes known the moment you assign it a number. Naturally, when you look up at the night sky and wonder how far it extends, you reach for the same instinct. You want a ruler long enough to stretch from here to there. You want a number that tells you the size of everything. This instinct works perfectly at human scales. The moon sits roughly 239,000 miles from Earth. We know this with extraordinary precision because Apollo astronauts left reflective mirrors on the lunar surface, and scientists bounce laser pulses off those mirrors and time the return trip. The measurement is clean, verified, repeatable. The distance to the Sun is approximately 93 million miles, a number refined over centuries through geometric calculation, planetary transits, and eventually radar ranging. These are real distances. You can point at the moon. You can point at the Sun. The gap between you and those objects behaves the way distance is supposed to behave. It is a stretch of empty space. You could, in principle, cross it. This is where your intuition begins to build a model of the universe. The model says space is a container. Objects sit inside it at various distances. If you had a fast enough ship, you could fly to any of them. The universe, in this model, is like an ocean. Vast, maybe incomprehensibly vast, but navigable. There is always a route from here to there. All you need is time. That model is about to break. Let us start where every cosmic journey begins. Earth orbits the Sun at a distance of roughly 93 million miles, a measurement astronomers call 1 astronomical unit. This is the yardstick for everything else in the solar system. Mars, at its closest approach, sits about 34 million miles away. At its farthest, when the Sun stands between us, the gap stretches to 250 million miles. Jupiter orbits at roughly 484 million miles from the Sun. Saturn sits at approximately 886 million miles. Neptune, the outermost major planet, circles at about 2.8 billion miles. These distances are enormous by any human standard, but they remain comprehensible in principle. Spacecraft have crossed them. Voyager 1, launched in 1977, has travelled roughly 16 billion miles from Earth. That is approximately 170 astronomical units. It took nearly half a century to get there, and it is still inside the Sun's gravitational influence, still technically within the outermost boundary of the solar neighbourhood. But it is out there, moving, proving that the solar system, while vast, is traversable with patience and engineering. Now take the next step. Leave the solar system entirely and look toward the nearest star. Alpha Centauri sits approximately 4.2 light-years away. 1 light-year equals roughly 5.88 trillion miles. Multiply that by 4.2 and you get approximately 24.7 trillion miles. Suddenly, the numbers stop meaning anything to your intuition. You can write 24 trillion on paper, but your brain cannot visualize it. No analogy fully captures it. You cannot feel the difference between 1,000,000,000,000 and 1,000,000,000 the way you can feel the difference between 10 and 100. The number exists, but it does not land. Here is what it means in practical terms. Voyager 1, the fastest object humanity has ever launched on a trajectory out of the solar system, travels at roughly 38,000 miles per hour. At that speed, reaching Alpha Centauri would take approximately 74,000 years. That is longer than all of recorded human civilization, longer than the existence of anatomically modern humans in Europe. The ship would arrive at a star whose light, travelling at the fastest speed the universe allows, covers the same distance in just over 4 years. Light crosses the gap in 4 years. Our best spacecraft would need 74,000. This ratio captures something essential about interstellar space. The distances between stars are not merely large, they are large in a way that makes human travel effectively impossible with any technology we currently possess. And Alpha Centauri is the closest star to us, the nearest one, the next-door neighbour. Scale up again. The Milky Way galaxy contains roughly 200 to 400 billion stars spread across a disk approximately 100,000 light-years in diameter. Our solar system sits about 26,000 light-years from the galactic centre, embedded in one of the spiral arms. From our position, the centre of the galaxy is hidden behind thick clouds of gas and dust that block visible light. We cannot even see the heart of our own galaxy without using infrared or radio telescopes to peer through the obstruction. To cross the Milky Way at the speed of light, you would need 100,000 years. No shortcut, no faster route. Light itself, the fastest phenomenon in physics, takes 100 millennia to make the trip. And during that journey, the galaxy rotates beneath you. Our solar system completes one orbit around the galactic centre approximately every 230 million years. The galaxy is not a static map you can chart and set aside. It is a spinning structure, and by the time light crosses it, the stars have rearranged themselves into entirely different configurations. Even within our own galaxy, distance imposes a kind of isolation that most people never consider. A signal sent from Earth at the speed of light would take 26,000 years to reach the galactic centre. If anyone there received it and sent a reply at the same speed, the round trip would take 52,000 years. No conversation could survive that delay. No exchange of ideas, no diplomacy, no shared discovery. Our galaxy is not a community. It is a scattering of isolated neighbourhoods separated by gulfs too wide for meaningful contact on any timescale humans can comprehend. But the Milky Way is not floating alone. Our galaxy belongs to a gravitational family called the Local Group, a collection of more than 50 galaxies bound together by mutual gravitational attraction. The Local Group spans roughly 10 million light-years and is dominated by two large spirals, the Milky Way and Andromeda, surrounded by a retinue of smaller satellite galaxies. The Large Magellanic Cloud, visible as a cloudy smudge from the southern hemisphere, orbits us at about 160,000 light-years. The Sagittarius dwarf galaxy, much closer, is actively being torn apart and consumed by the Milky Way's tidal forces. These companion galaxies are our nearest cosmic neighbours, close enough that gravity holds the entire group together against the expansion of space. Step farther out, and the Local Group itself becomes a small feature within a much larger structure. Roughly 54 million light-years away lies the Virgo cluster, a massive concentration of over 1,300 galaxies bound together by an enormous reservoir of dark matter. The Virgo cluster is not merely a collection of galaxies, it is a gravitational anchor for everything in our region of space. The Milky Way, along with the rest of the Local Group, is falling toward Virgo at roughly 250 kilometers per second, pulled by a gravitational influence that reaches across tens of millions of light-years. And even the Virgo cluster is only one node in something vastly larger. In 2014, astronomers mapped the gravitational flows of thousands of galaxies in our cosmic neighbourhood and discovered that the Milky Way, the local group, the Virgo cluster, and tens of thousands of other galaxies all belong to a single enormous gravitational basin called the Laniakea supercluster. Laniakea spans approximately 500 million light-years and contains roughly 100,000 galaxies, all streaming toward a gravitational focal point called the Great Attractor. The name Laniakea comes from Hawaiian and means immeasurable heaven, which is an understatement. But superclusters are not the largest structures. They are merely components of the cosmic web, the grandest architecture in nature. If you could step far enough outside the universe to see its large-scale structure, you would not see galaxies scattered randomly through space. You would see a vast three-dimensional network of filaments, walls, and nodes, with galaxies concentrated along the filaments and enormous empty voids occupying the spaces between them. The filaments stretch for hundreds of millions of light-years, thin threads of matter connecting galaxy clusters at the intersections. The voids between them can span 300 million light-years or more, containing almost nothing. The overall pattern resembles the structure of a sponge or the network of neurons in a brain, with dense concentrations of matter separated by vast empty bubbles. This cosmic web is not a random arrangement. It is the direct consequence of tiny density variations in the early universe, quantum fluctuations from the first fraction of a second after the Big Bang, amplified over billions of years by gravity. Regions that started slightly denser attracted more matter, growing into filaments and clusters. Regions that started slightly less dense lost matter to their neighbours, becoming the voids. The entire large-scale structure of the universe is a gravitational fossil, a record of initial conditions written in the distribution of hundreds of billions of galaxies across billions of light-years. And here is the critical point for the story of cosmic distance. Galaxies are not evenly sprinkled through space. They are organized into structures, spanning hundreds of millions of light-years. The distances between these structures are not empty in the way that the space between stars is empty. They are defined by the architecture of the cosmic web, a framework so vast that light needs hundreds of millions of years to cross a single filament. The universe at these scales is not a featureless expanse waiting to be crossed. It is a structured landscape of matter and emptiness, extending in every direction to the limits of what we can observe, and almost certainly far beyond. This is the stage on which the rest of the story plays out. Not a simple void dotted with isolated galaxies, but a vast, organized, hierarchical web of matter stretching to the edge of the observable universe and beyond. And the distances within that web are about to become far stranger than anything the Milky Way or the local group could prepare you for. All of this structure, the filaments, the clusters, the voids, exists at distances where a new problem emerges. Distance stops being purely spatial and becomes temporal. To see why, come back down from the cosmic web to something closer, something you can observe with your own eyes. Andromeda, the nearest major galaxy to our own, sits roughly 2.5 million light-years away. On a clear autumn night in the northern hemisphere, you can see it with your naked eye. It appears as a faint smudge of light in the constellation that shares its name. That smudge contains approximately 1 trillion stars. It is larger than our galaxy, more massive, and it is heading toward us at roughly 250,000 miles per hour. 2.5 million light-years. Think about what that distance means in practice. The light arriving at your eyes from Andromeda tonight left that galaxy 2.5 million years ago. When those photons began their journey, the genus Homo was just appearing on the African continent. Early human ancestors were chipping stones into crude tools. Saber-toothed cats stalked grasslands that would eventually become modern cities. The entire arc of human civilization, every empire, every war, every poem, every scientific breakthrough, every person you have ever known or heard of, fits inside the travel time of that faint smudge of light. When you look at Andromeda, You are not seeing it as it exists right now. You are seeing a 2.5 million year old version of it. The galaxy you observe tonight is a ghost image, a portrait painted in ancient photons. The real Andromeda, the one that exists at this very moment, is invisible to you. Its current light has not arrived yet and will not arrive for another 2.5 million years. This is the first crack in the cosmic ruler. At small scales, distance is just distance. The moon is 239,000 miles away, and that statement describes a gap in space that exists right now in the present moment. You and the moon share the same slice of time, but Andromeda is 2.5 million light years away, and that statement does not merely describe a gap in space, it describes a gap in time. You and Andromeda do not share the same present. You see its past. If observers in Andromeda were looking at us, they would see our past. The distance between you is not merely spatial, it is temporal, and the farther you look, the deeper into the past you see. This is not a metaphor, it is not a poetic flourish. It is a physical consequence of the fact that light travels at a finite speed. Every photon carries a timestamp. When it arrives at your telescope, it tells you not what a distant object looks like now, but what it looked like when the light departed. The object may have changed dramatically since then. It may have moved. Stars within it may have been born and died. The version you observe is a fossil preserved in light, and you have no way of knowing what that object looks like in its actual present, because the information about its current state has not reached you yet. At nearby distances, this time delay is negligible. Light from the moon reaches Earth in about 1.3 seconds. Light from the sun takes approximately 8 minutes. These delays are real but practically insignificant. You see the moon as it was just over a second ago, close enough to the present that it makes no meaningful difference for any observation you could perform. But at galactic and intergalactic distances, the delay becomes enormous. Light from the center of the Milky Way takes 26,000 years to reach us. Light from Andromeda takes 2.5 million years. And as you look farther, the delay grows without limit. A galaxy 1 billion light years away appears as it was 1 billion years ago. A galaxy 10 billion light years away appears as it was 10 billion years ago, long before our solar system existed, long before the sun ignited, long before the atoms in your body had assembled into a planet. This means that looking across the universe is not like looking across a room. When you look across a room, everything you see exists in the same moment. The chair, the wall, the window, all of them share your present. When you look across the universe, nothing shares your present except the objects closest to you. Everything else is displaced in time. The farther the object, the older the image. The deepest observations astronomers have ever made show galaxies as they existed billions of years before Earth formed. Every direction you look, every distance you measure, you are peeling back layers of time like sediment in geological strata, except the layers are made of light and they extend for billions of years. Astronomers call this phenomenon look-back time. The look-back time to an object is the duration that light from that object has spent travelling to reach you. It equals the distance in light years, measured as a travel duration rather than a spatial gap. Look-back time transforms the telescope into something almost magical. Not a machine that carries you into the past, but one that lets you witness the past from the present, frozen in photons that have been crossing the void since the events they depict actually occurred. Every observation of a distant galaxy is an act of archaeology. You are studying a ruin that no longer exists in the form you see it, reconstructed from evidence that took billions of years to arrive. This is where the familiar distance ladder begins to bend under the weight of what it reveals. Astronomers measure cosmic distances using a sequence of techniques, each one building on the previous, each one reaching farther but also introducing new uncertainties. The first rung is parallax, the apparent shift in a nearby star's position as Earth orbits the Sun. By measuring how much a star appears to move against the background of more distant stars over the course of 6 months, astronomers can calculate its distance using straightforward geometry. Parallax works beautifully for stars within a few thousand light years, but beyond that, the apparent shift becomes too small to measure accurately even with the most precise instruments available. The second rung uses Cepheid variable stars. These are giant pulsating stars whose brightness fluctuates in a regular cycle. In 1912, astronomer Henrietta Leavitt discovered that the period of a Cepheid's brightness cycle is directly related to its intrinsic luminosity. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. This relationship means that if you observe a Cepheid in a distant galaxy and measure its pulsation period, you know how intrinsically bright it truly is. Compare that true brightness to how dim it appears from Earth, and you can calculate how far away it must be. Cepheids extend the distance ladder out to roughly 100 million light-years, bridging the gap from our local galactic neighborhood to nearby galaxy clusters. Beyond that range, astronomers rely on Type 1a supernovae. These are thermonuclear explosions that occur in specific binary star systems, and they all reach approximately the same peak brightness. This consistency makes them reliable standard candles. Observe a Type 1a supernova in a distant galaxy. Compare its apparent brightness to its known intrinsic brightness, and you can calculate how far away that galaxy sits. This technique reaches billions of light-years into the cosmos, pushing the distance ladder to its most extreme limits and revealing the large-scale structure and expansion history of the universe. But here is the critical point that transforms everything. Every rung of this ladder measures light. Every technique depends on photons traveling from a distant source to an observer on or near Earth. And every one of those photons carries the imprint of the time it spent in transit. The farther the source, the longer the journey, the older the information. When astronomers used these techniques to measure the distances to increasingly remote galaxies in the early 20th century, they discovered something that changed our understanding of reality. In 1929, Edwin Hubble published observations showing that distant galaxies are moving away from us, and that the farther a galaxy is, the faster it recedes. This was the first direct evidence that the universe is expanding. Hubble's discovery did not just add a fact to the textbook, it demolished the static model of the cosmos that had dominated human thinking for millennia. The universe was not a fixed container with objects scattered inside it at permanent addresses. The universe was growing. Space itself was stretching, and this stretching had consequences for distance that nobody at the time fully grasped. If space is expanding, then the distance between any two widely separated objects increases over time. Not because those objects are moving through space like ships across an ocean, but because the space between them is growing. This is fundamentally different from ordinary motion. A car driving away from you moves through a fixed road. A galaxy receding due to cosmic expansion is not moving through space at all in the conventional sense. The fabric of space between you and that galaxy is literally being created, moment by moment, stretching the gap wider without either object changing its local position. At small scales, this expansion is negligible. The space between you and the Moon is not expanding in any measurable way because gravity holds the Earth-Moon system together. The space within our solar system, within our galaxy, even within our local cluster of galaxies, is dominated by gravitational forces that overpower the cosmic expansion. But at cosmological scales, across hundreds of millions of light-years and beyond, expansion dominates gravity, and the effects are staggering. Consider what expansion means for the light travelling toward you from a very distant galaxy. That light left the galaxy billions of years ago. During its entire journey, space was expanding. The galaxy was getting farther away even as the light was crossing the gap. By the time the light arrives at your telescope, the galaxy is no longer where it was when the photons were emitted. It is much, much farther away. carried outward by the relentless stretching of space. This is why the observable universe is so much larger than 13.8 billion light-years in any direction, despite the universe being only 13.8 billion years old. Light from the most distant observable sources began its journey nearly 13.8 billion years ago, but during that journey, the expansion of space stretched the distance between source and observer enormously. The objects that emitted that ancient light now sit approximately 46.5 billion light-years away, not because they traveled through space at impossible speeds, but because space itself expanded beneath them while the light was in transit. The universe grew around the photons as they traveled. This single fact shatters the simple ruler model of the universe. You cannot draw a line from here to the farthest observable object and treat it as a fixed distance you could someday cross. That distance was shorter when the light was emitted. It is longer now, and it will be even longer tomorrow. The ruler is not static, it is growing. The gap you are trying to measure changes while you measure it, stretching faster the farther out you look. Even more unsettling, this expansion means that the light you see from the most distant galaxies does not tell you where those galaxies are right now. It tells you where they were billions of years ago, when the light departed. The galaxy's current position is unknowable in any practical sense. By the time you could send a signal asking where it has gone, the galaxy would have moved even farther away. The signal itself might never arrive. The question would die in transit, swallowed by the expanding void. This is the point where ordinary distance collapses as a useful concept for describing the cosmos. In your everyday experience, distance is a relationship between 2 points that exist at the same time. You and the grocery store both exist right now, and the 2 miles between you is a gap you can cross. But when you look across the universe, the distance you measure connects 2 different moments in time. You exist now. The distant galaxy you observe existed billions of years ago. The space between you is not a gap you could cross, because the destination you see no longer exists in the form you are observing it. The real galaxy, whatever it looks like today, sits in a location you cannot determine, at a distance that has been growing for the entire duration of the light's travel. The universe, at its largest scales, does not behave like an ocean you could sail across given enough time. It behaves like an ocean that expands faster than your ship can sail, an ocean where the far shore retreats as you approach, an ocean where the charts redraw themselves while you navigate. And we have not even reached the truly disturbing part yet. Everything described so far applies to objects we can still see. Photons from those distant galaxies did eventually reach us. Ancient light, stretched and weakened by billions of years of expansion, but it arrived. We detected it, we measured it, we catalogued it. But what about the light that never arrives? What about the regions of space so far away, receding so rapidly that their light can never reach Earth? Not in a billion years, not in a trillion, not ever. What about the parts of the universe that we can observe in ancient photons, but can never touch, never visit, never send even a single message to? The cosmic ruler does not just stretch. Beyond a certain point, it snaps entirely. And when it does, the idea that the universe is a single connected space that humanity could someday explore collapses into something far stranger and far more isolating than most people have ever considered. That boundary, that breaking point where distance stops being a measurement and becomes a permanent barrier, is what comes next. Push the look-back concept from earlier to its absolute limit. If looking at a galaxy 1 billion light-years away means seeing 1 billion years into the past, and looking at a galaxy 10 billion light-years away means seeing 10 billion years into the past, then what happens when you look as far back as possible? What do you find at the end of the line? You do not find the edge of the universe. You do not find the Big Bang sitting at some fixed point in the distance like a monument at the end of a highway. What you find is a wall. Not a physical barrier made of matter or energy, but a wall made of light itself, ancient light. the oldest light in the observable universe, and it surrounds you in every direction, uniformly, without a gap. This wall is the cosmic microwave background, and understanding what it is not, and why it exists is the key to understanding why distance across the universe is fundamentally different from any distance you have ever experienced. To understand the cosmic microwave background, you need to go back to the very early universe, not to the first second or the first minute, but to the first few 100,000 years after the Big Bang. During this era, the universe was unimaginably hot and dense. Temperatures exceeded thousands of degrees. Matter existed not as atoms, but as a seething plasma of free protons, free electrons, and photons of light, all crammed together and interacting constantly. In this plasma, light could not travel freely. Every photon that moved in any direction almost immediately collided with a free electron and scattered off in a random new direction. The universe was opaque. Not dark, the opposite. It was blazing with energy, glowing hotter than the surface of most stars. But none of that light could travel any meaningful distance because the free electrons blocked its path. Imagine being inside an incredibly dense, luminous fog that extends in every direction without end. You cannot see through it. Every photon is absorbed and re-emitted within a tiny fraction of a second. No information can propagate, no signal can escape. The universe at that stage was a prison of light, trapping its own radiation within itself. To grasp how thoroughly light was trapped, consider the interior of our own sun. A photon generated by nuclear fusion in the sun's core does not travel straight to the surface. It is absorbed and re-emitted by dense plasma, knocked off course with every interaction, wandering randomly through the solar interior in a process physicists call a random walk. A single photon takes an estimated 170,000 years to migrate from the core to the surface, not because the sun is especially large, but because the photon cannot travel more than a fraction of a centimeter before hitting another particle. The early universe was like the inside of a star, except there was no surface to reach. The plasma extended everywhere. There was no transparent region to escape into. Every direction was deeper interior. This state persisted for approximately 380,000 years after the Big Bang. Then something happened that changed everything. As the universe expanded, it cooled. Expansion stretches space, and stretching space dilutes the energy within it. Temperatures drop steadily over hundreds of thousands of years. And at a critical threshold, roughly 3000 Kelvin, the universe cooled enough for a profound transition to occur. Protons and electrons, which had been too energetic to combine, suddenly began binding together into neutral hydrogen atoms. Physicists call this moment recombination, even though it was technically the first time protons and electrons combined, not a recombination. The terminology is a historical accident, but the event itself was transformative. When electrons joined with protons to form neutral atoms, they were no longer free to scatter photons. Neutral hydrogen is largely transparent to the wavelengths of light that filled the early universe. Suddenly, after 380,000 years of imprisonment, light could travel freely. Photons that had been bouncing endlessly between charged particles were released all at once across the entire cosmos. They streamed outward in every direction, carrying with them a snapshot of the universe at the moment of their liberation. Those photons have been travelling ever since. For approximately 13.8 billion years, they have crossed the expanding universe, stretched by the growth of space from their original infrared and visible wavelengths into the microwave range. When they arrive at Earth today, they carry a temperature of approximately 2.7 Kelvin, just a few degrees above absolute zero. They arrive from every direction in space with almost perfect uniformity, varying by only about 1 part in 100,000 from one patch of sky to another. This is the cosmic microwave background, It is not a place. It is not an object. It is a surface in time, the last moment when the universe was opaque, preserved in photons that have been crossing space since before any star or galaxy existed. When you detect the cosmic microwave background, you are observing the universe as it was 380,000 years after the Big Bang, not as it is now, not as it was at any other moment. Specifically, precisely, exclusively, at the instant when light first broke free. And here is the first critical misconception that must be dismantled. Many people, when they learn about the cosmic microwave background, form a mental picture of it as the Big Bang itself, sitting at the far edge of the universe like a glowing wall at the end of a corridor. They imagine that if they could somehow travel far enough, they would reach this wall and find the place where everything began. The cosmic microwave background, in this picture, is the outer shell of the cosmos, the physical boundary where space terminates and the creation event sits frozen in time. This picture is completely wrong. The cosmic microwave background is not the Big Bang. The Big Bang was not an event that happened at a specific location in space. There is no point you could travel to and say this is where the Big Bang occurred. The Big Bang was the rapid expansion of space itself, happening everywhere simultaneously. Every point in the universe, including the spot where you are sitting right now, was part of the Big Bang. The hot, dense plasma that filled the early cosmos was not concentrated in one place. It was everywhere. The entire universe, as far as it extended, was filled uniformly with this searing plasma. When recombination occurred and light broke free, it happened everywhere at once. Photons were released at every location in the universe simultaneously. The reason you detect the cosmic microwave background coming from a specific distance, approximately 46.5 billion light-years away in every direction, is not that the Big Bang happened at that distance. It is that light from that distance has taken 13.4 billion years to reach you. The photons arriving today were released at recombination from matter that was, at the time, much closer to us. But during the approximately 13.8 billion years those photons have been travelling, the space between their origin and Earth has expanded enormously. The matter that emitted those photons now sits 46.5 billion light-years away, not because it moved through space, but because space itself grew beneath it. Every observer in the universe, no matter where they are, detects the cosmic microwave background surrounding them uniformly in every direction. An astronomer on a planet orbiting a distant star in another galaxy would see the same cosmic microwave background arriving from the same look-back time, surrounding them in a sphere of ancient light centered on their own location. Their sphere would overlap with ours but extend into regions we cannot see. The cosmic microwave background is not an edge. It is a horizon, a limit of visibility created by the finite speed of light and the finite age of the universe. Beyond it, the universe continues. More matter, more space, more structure. But the light from those more distant regions has not had time to reach any observer. It is still in transit, or it was emitted before recombination when the universe was opaque, meaning it was scattered and absorbed long before it could travel freely. This distinction between a horizon and an edge is crucial. An edge implies that space ends, that if you travelled far enough, you would hit a wall, a boundary, a final surface beyond which nothing exists. The cosmic microwave background is not that. It is the farthest back in time that electromagnetic radiation allows us to see, but it is not the farthest extent of space. Space almost certainly continues beyond the cosmic microwave background, extending much farther than the observable region, possibly infinitely. We simply cannot see it. The light from those regions either has not arrived yet or was never able to travel freely in the first place. The observable universe, defined as the sphere of space from which light has had time to reach us since the Big Bang, is therefore not the entire universe. It is merely the part we can observe. The distinction matters enormously. When someone says the observable universe is 93 billion light-years in diameter, they are describing the size of our cosmic horizon, not the size of everything that exists. The actual universe, the whole thing, whatever shape it takes, whatever extent it has, could be vastly larger. Some cosmological models, based on precise measurements of the cosmic microwave background's geometric properties, suggest the entire universe is at least 250 times larger than the observable volume. Others permit an infinite universe extending without limit in all directions. We do not know. We may never know. The answer lies beyond our horizon, permanently inaccessible to direct observation. The claim that the universe extends far beyond the observable volume is not speculation. It rests on one of the most precisely measured quantities in cosmology: the curvature of space. In general relativity, space can have three possible large-scale geometries. It can be positively curved, like the surface of a sphere, where parallel lines eventually converge and the angles of a triangle add up to more than 180 degrees. It can be negatively curved, like a saddle, where parallel lines diverge and triangles contain less than 180 degrees. Or it can be flat, where parallel lines remain parallel forever and triangles behave exactly as Euclidean geometry predicts. A positively curved universe would wrap around on itself and have a finite total volume, much the way the surface of the Earth is finite even though it has no edge. A flat or negatively curved universe would extend without limit in all directions. Measurements of the cosmic microwave background, primarily from the European Space Agency's Planck satellite, have determined the curvature of space to extraordinary precision. The result is consistent with perfect flatness, with an uncertainty of less than 0.5%. Space is flat, or so close to flat that any curvature, if it exists, operates on scales enormously larger than the observable universe. This flatness is the reason cosmologists believe the universe extends far beyond what we can see. If the universe were only slightly larger than the observable volume, its curvature would be detectable. The fact that we measure no curvature at all implies that the full universe dwarfs the observable region. Some estimates based on the Planck data suggest the entire universe is at least 250 times larger in radius than the observable universe. Others permit an infinite extent. Either way, the 93 billion light-year diameter of the observable universe is not the size of everything. It is the size of our window, and the building beyond the window may have no walls at all. This leads to a question the audience is almost certainly asking. If the observable universe is not the whole universe, and the whole universe extends far beyond what we can see, does the whole universe have an edge? Is there a wall somewhere out there, a final boundary, a surface where space simply stops? As far as current physics can determine, no. The universe has no known edge. It has no outer wall. It has no farthest point that a traveller could reach and say this is the end. If the universe is infinite, as a flat geometry permits, then it extends without limit in every direction. You could travel in a straight line forever and never reach a boundary. There is always more space ahead of you, populated by more matter, more galaxies, more structure, stretching onward without end. The universe in this scenario is not a container with contents inside it. It is the contents, extending in all directions, with no exterior and no edge. If the universe is finite, it is almost certainly finite but unbounded, meaning it curves back on itself in a higher dimensional geometry. The closest analogy is the surface of a sphere. An ant walking across the surface of a globe can walk forever in a straight line and never reach an edge. The surface is finite in area but has no boundary. It wraps around. A finite universe would work the same way in 3 dimensions. You could travel in a straight line and eventually return to where you started, having circumnavigated a cosmos that is finite in volume but has no wall, no border, no endpoint. Either way, the concept of across the universe has no defined destination. There is no farthest point to aim for. The cosmic ruler you imagined at the start of this journey does not merely stretch or snap, it has nowhere to land. Now consider what this means for the concept of distance. When you say the observable universe is 93 billion light-years across, you are quoting its co-moving diameter. Co-moving distance is a measure that accounts for cosmic expansion. It describes how far apart two objects are right now, at this very moment in cosmic time, factoring in all the stretching of space that has occurred since the light was emitted. This is the most physically meaningful definition of distance on cosmological scales, but it is also the most counterintuitive. The light travel distance to the edge of the observable universe is approximately 13.8 billion light-years. That is the raw amount of time the oldest photons spent traveling to reach us. But the comoving distance to the matter that emitted those photons is approximately 46.5 billion light-years. During that approximately 13.8 billion year journey, space expanded by a factor of roughly 1,100, stretching the original separation into something far larger than the travel time alone would suggest. These two numbers, 13.8 billion and 46.5 billion, measure the same gap. They are not contradictory. They are two different ways of describing the same relationship between source and observer, one measured as travel time, the other as current physical separation. But the difference between them reveals something profound. The gap between you and the most distant observable objects is not fixed. It was smaller in the past and will be larger in the future. The distance you measure depends on when you measure it, and the answer changes continuously as space expands. Look-back time, comoving distance, and light travel distance are three separate concepts that all describe aspects of cosmic separation, and conflating them leads to confusion. Look-back time tells you how long ago the light was emitted. Light travel distance tells you the spatial span the photon crossed during its journey. Co-moving distance tells you how far apart the source and observer are right now. At cosmological scales, these three numbers can be wildly different from each other. Understanding why they diverge is essential to understanding why distance across the universe does not work like distance across a city. Astronomers have been pushing the boundaries of observation closer and closer to the cosmic microwave background, trying to see the most ancient galaxies that formed in the earliest epochs of cosmic history. For decades, this frontier advanced slowly. Distant galaxies are faint, tiny, and their light has been stretched into infrared wavelengths that ground-based telescopes struggle to detect. The Hubble Space Telescope extended our reach dramatically, but even Hubble had limits. Then the James Webb Space Telescope began operations in 2022, and the frontier exploded outward. The James Webb Space Telescope was designed specifically to detect infrared light from the most distant and ancient objects in the universe. Its 6.5-meter gold-plated mirror collects vastly more light than Hubble's 2.4-meter mirror, and its infrared instruments are sensitive to exactly the wavelengths where the most distant galaxies emit their red-shifted photons. Within its first years of operation, the telescope shattered record after record for the most distant galaxy ever observed. In 2024, a team using the James Webb Space Telescope's near-infrared spectrograph confirmed a galaxy called Jade's GSZ 14-0 at a redshift of approximately 14.32. This galaxy existed just 290 million years after the Big Bang. Its light had been travelling for over 13.5 billion years before reaching the telescope's detectors. When that light was emitted, the universe was a fraction of its current age, and the first generation of stars was just beginning to illuminate the cosmos. Then, in 2025, the telescope broke its own record again. A galaxy designated MOM-Z14 was confirmed at a redshift of 14.44, corresponding to just 280 million years after the Big Bang. This is currently the most distant spectroscopically confirmed galaxy known to humanity. According to NASA, the galaxy is brighter, more compact, and more chemically enriched than astronomers predicted for such an early era. It shows elevated levels of nitrogen, suggesting that massive stars had already formed and evolved rapidly in the dense conditions of the young universe. The galaxy had even begun clearing the neutral hydrogen gas in its surrounding region, a process that was not expected to be underway so early. These discoveries are remarkable not only for their distance but for what they reveal about cosmic history. The universe, at 280 million years old, was supposed to be a simpler place, populated by small, dim proto-galaxies gradually assembling their first stars. Instead, the James Webb Space Telescope keeps finding objects that are unexpectedly luminous, unexpectedly massive, and unexpectedly mature. The early universe was more complex than standard models predicted. Something in our understanding of how galaxies form may need revision. It is essential to understand what the James Webb Space Telescope is actually doing when it breaks these records. It is not seeing farther across the universe in the way a more powerful pair of binoculars lets you see a more distant hilltop. It is seeing deeper into the past. Each new redshift record is not a spatial conquest but a temporal one. When astronomers celebrate reaching redshift 14, they are celebrating the ability to witness an era of cosmic history that was previously invisible, a time so early that the universe had completed barely 2% of its current age. The galaxies the telescope detects at these redshifts are not sitting at the farthest edge of some cosmic map. They are sitting at the earliest accessible layer of cosmic time, preserved in photons that have been travelling for over 13 billion years. But from the perspective of cosmic distance, these observations illustrate the look-back principle pushed to its extreme. When you observe MOMZ 14, you are seeing an object as it existed 280 million years after the Big Bang. The light from that galaxy spent over 13.5 billion years crossing space to reach us. During that journey, the universe expanded enormously. The galaxy that emitted this light now sits at a comoving distance of roughly 36 billion light-years from Earth. You can see it, but the object you observe is a phantom, an image of something that existed over 13 billion years ago in a location now separated from you by a chasm that has been growing every second since the photons departed. The light arrived, the source did not stay. The James Webb Space Telescope cannot see past the cosmic microwave background. No electromagnetic telescope ever will. The cosmic microwave background represents the farthest reach of light-based observation, a hard boundary imposed by the physics of recombination. Before 380,000 years after the Big Bang, the universe was opaque. Photons from that era were absorbed and re-emitted so many times that they carry no coherent information about specific locations or events. They became thermalized, blended into a smooth glow that tells us the average temperature and density of the early universe, but nothing about individual structures. To probe beyond the cosmic microwave background, astronomers would need to detect something other than electromagnetic radiation. Gravitational waves, which are ripples in space-time caused by massive accelerating objects, travel freely through matter and would not have been blocked by the opaque plasma of the early universe. In principle, a sufficiently sensitive gravitational wave detector could pick up signals from the inflationary epoch, the first tiny fraction of a second after the Big Bang, when the universe expanded exponentially and generated primordial gravitational waves that should still permeate space. Neutrinos, which interact with matter so weakly that they pass through virtually anything, would also have been streaming freely through the early universe long before photons could. The cosmic neutrino background, a relic population of neutrinos from roughly 1 second after the Big Bang, should exist everywhere in the universe. But its energy is so low that no current instrument can detect it. Each of these represents a potential window into epochs of cosmic history that the cosmic microwave background permanently conceals. The cosmic neutrino background is the older of the two. Neutrinos are subatomic particles that interact with matter so weakly that trillions of them pass through your body every second without disturbing a single atom. In the early universe, roughly 1 second after the Big Bang, the cosmos cooled enough that neutrinos decoupled from the rest of matter and radiation. They stopped interacting and began streaming freely through space, carrying a snapshot of the universe at an age of 1 second. That is 379,999 years earlier than the cosmic microwave background. A neutrino telescope sensitive enough to detect these primordial particles would see the universe as it was when nuclear fusion was occurring throughout all of space. When protons and neutrons were assembling into the lightest atomic nuclei, the cosmic neutrino background exists. It fills every cubic centimeter of the universe, with an estimated density of roughly 330 neutrinos per cubic centimeter. But their energy has been redshifted to extraordinarily low values by 13.8 billion years of cosmic expansion, and no detector built or proposed can capture them at these energies. The window exists. The glass is too thick to see through. Primordial gravitational waves offer an even more dramatic possibility. During cosmic inflation, the exponential expansion that is thought to have occurred in the first tiny fraction of a second after the Big Bang, quantum fluctuations in space-time itself would have been stretched to cosmic scales, generating gravitational waves that should still permeate the universe. These waves would carry information from an era so early that the universe had not yet produced protons, neutrons, or any form of matter as we know it. Detecting them would let us observe the universe at an age measured in fractions of a trillionth of a second. Several experiments, including ground-based observatories and proposed space missions, are actively searching for the signature of primordial gravitational waves imprinted on the polarization of the cosmic microwave background. As of now, no confirmed detection has been made, but the search continues because the payoff would be extraordinary. It would let us peer behind the wall of ancient light into the very mechanism that made the observable universe as large as it is. For now, these windows remain closed or barely cracked. The cosmic microwave background is still the practical boundary of electromagnetic observation, and this wall carries a message that most people misunderstand. The cosmic microwave background is often described as the afterglow of the Big Bang, and that description is technically accurate but deeply misleading if taken too literally. It suggests that the Big Bang is a discrete event that happened long ago and far away, and that the afterglow is its residual signature, like the fading warmth of a campfire hours after the flames went out. This framing implies distance. It implies that the Big Bang is located somewhere out there, and the cosmic microwave background is the last visible evidence of it, sitting at the edge of the known universe like a faded photograph pinned to a distant wall. The truth is stranger. The Big Bang did not happen out there. It happened here, and there, and everywhere. The matter that emitted the cosmic microwave background photons now arriving at Earth was once right where you are sitting. 13.8 billion years ago, the matter that would become you, the matter that would become the Earth, the matter that would become the Sun and the Milky Way and Andromeda and every galaxy in every direction, was all compressed into a state of extreme density and temperature that filled the entire universe. There was no empty space surrounding this dense region. The dense region was the universe, all of it, as far as it extended, which may have been infinite even then. When the universe expanded and cooled, and recombination occurred, and light broke free, it did so everywhere. Photons were released from every point in the cosmos. Most of those photons travelled away from where you are now, heading outward into space, and you will never detect them. The photons you detect as the cosmic microwave background are the ones that were released from matter far enough away that their light is only now arriving, after approximately 13.8 billion years of travel. You are seeing the universe's distant past. But that distant past happened in the same universe, the same fabric of space-time that you currently occupy. The cosmic microwave background is therefore not a wall at the edge of the universe. It is a wall in time, a temporal horizon beyond which electromagnetic observation cannot penetrate. It surrounds every observer equally, receding as the universe ages, and it marks not the boundary of space but the boundary of visibility. Beyond this boundary, the universe almost certainly continues, Current measurements of the geometry of space, based on the angular patterns in the cosmic microwave background, show that space is flat to extraordinary precision. A flat geometry is consistent with a universe that extends far beyond the observable region, potentially without limit. The observable universe, 93 billion light-years across, may be a tiny fraction of the whole, or it may be a representative sample of something infinite. Either way, the vast majority of everything that exists is hidden from us, cut off not by a physical wall, but by the simple fact that light has not had enough time to make the trip. This changes what across the universe means. You cannot go across the universe because you do not know how far across it extends. The observable universe has a measurable diameter, but the observable universe is not the universe, it is a window, and windows do not show you the whole building. For the entire history of astronomy, humans have been looking through this window, cataloguing what they see, measuring distances, and building maps. Those maps are accurate within the observable volume, but they describe only the part of reality that light has revealed to us. What lies beyond the cosmic microwave background in spatial terms is unknown, and may remain unknown permanently, because the expansion of space pushes distant regions away from us faster than light can cross the growing gap. This raises a question that transforms everything about cosmic distance. If the universe is expanding, and the expansion is accelerating, and the distances to the most remote observable objects are already almost incomprehensibly vast, then how much of what we can see is actually within our reach? How much of the observable universe could we, even in principle, ever visit, communicate with, or interact with in any meaningful way? The answer is far less than you think, and the reason involves a boundary even more disturbing than the cosmic microwave background, a boundary not of visibility, but of causality itself. In 1929, Edwin Hubble published a graph that quietly demolished the human assumption of a stable, fixed cosmos. The graph plotted the distances to nearby galaxies against their recession velocities, and the relationship was linear. The farther a galaxy was, the faster it was moving away. Double the distance, double the speed. Triple the distance, triple the speed. Every galaxy in every direction was receding from us, and the rate of recession scaled directly with separation. This observation, now formalized as Hubble's law, was the first direct evidence that the universe is expanding. But the nature of that expansion is almost universally misunderstood, and correcting that misunderstanding is essential to grasping why distance across the universe collapses into something far stranger than a very large number. When you throw a ball across a field, the ball moves through space. It has a velocity. It leaves your hand, travels a trajectory, and arrives somewhere else. The space between you and the landing spot does not change. The field stays the same size. The ball crosses a fixed gap. This is ordinary motion, the kind governed by Einstein's special relativity, and it has a hard speed limit. Nothing traveling through space can exceed the speed of light. No particle, no signal, no spacecraft, no information of any kind. That speed limit is absolute. It is the fastest anything can move from one place to another within the fabric of space. Hold on to this distinction, because what comes next violates every expectation it creates. When most people hear that galaxies are moving away from us, they picture objects flying outward through space, like shrapnel from a detonation. They imagine galaxies as projectiles launched from a central point, racing through a pre-existing void. In this mental model, the galaxies have velocity, they are travelling through space, and the fastest ones have gotten the farthest away, which is why distant galaxies recede more quickly than nearby ones. This picture is wrong in almost every respect. Cosmic expansion is categorically different. The fabric of space-time itself is stretching. New space is being created between distant objects, not because anything is pushing them apart, but because the metric of space, the mathematical structure that defines distances, is increasing with time. Galaxies are not moving through space in the conventional sense. They are standing still in their local region of space-time, while the space between them grows. Think of it this way. Imagine a loaf of raisin bread dough rising in an oven. Each raisin represents a galaxy. As the dough expands, every raisin moves away from every other raisin. A raisin near the center sees all other raisins receding. A raisin near the edge sees the same thing. No raisin is at the center of the expansion. No raisin is moving through the dough. The dough itself is growing, and the raisins are carried along with it. The farther apart two raisins are, the more dough exists between them, and the faster that intervening dough expands. This is why distant galaxies recede faster than nearby ones. More space between you means more space expanding, which means a greater overall recession velocity. This is why recession velocities can exceed the speed of light without violating any law of physics. The speed of light limit applies to objects moving through space. It does not apply to space itself. Space has no speed limit on how fast it can expand. And when you add up the tiny increments of expansion occurring in every megaparsec between here and a very distant galaxy, the cumulative effect can produce recession velocities of 2, 3, even 4 times the speed of light. No object has exceeded the speed of light. No information is being transmitted faster than light. The expansion is not a signal or a motion. It is a change in the metric of space-time itself, and light cannot outrun the continuous generation of the medium it is travelling through. There is a direct physical consequence of this expansion that every astronomer relies on, and that you need to understand before the rest of this journey will make sense. When space expands, it does not merely move objects apart, it stretches everything embedded within it, including light. A photon travelling through expanding space has its wavelength physically lengthened during the journey, not because anything is pulling on the photon, not because the photon is losing energy through interaction with matter. The space the photon is moving through is itself getting longer, and the photon's wavelength stretches with it. A photon emitted as ultraviolet light from a young galaxy in the early universe might, after billions of years of travel through expanding space, arrive at Earth as visible light. After even more expansion, it might arrive as infrared. After enough expansion, it arrives as a microwave or a radio wave. The photon has been redshifted, its wavelength pushed toward the red end of the electromagnetic spectrum and beyond. This is cosmological redshift, and it is the single most important observable in the study of cosmic distance. When astronomers measure the redshift of a distant galaxy, they are directly measuring how much space has expanded between that galaxy and Earth during the time the light was in transit. A redshift of 1 means space has doubled in size since the light was emitted. A redshift of 10 means space has expanded by a factor of 11. The most distant confirmed galaxy has a redshift of more than 14. That means space has expanded by a factor of roughly 15 since that galaxy's light began its journey. The photons that departed as ultraviolet starlight arrived at the telescope as deep infrared radiation, stretched by the expansion of space across more than 13 billion years of cosmic history. Redshift is not merely a measurement of speed or distance. It is a measurement of how much the universe has grown during the lifetime of a single photon. Every photon from a distant source arrives at Earth carrying a record of the expansion it experienced. Understand that record, and you can reconstruct the expansion history of the universe. This is Hubble's law in its proper physical context. The recession velocity of a distant galaxy is not a measure of how fast that galaxy is travelling through space. It is a measure of how fast the space between you and that galaxy is growing. The constant of proportionality in Hubble's law, called the Hubble constant or h0, quantifies this expansion rate. It tells you how fast space is stretching per unit of distance. At this point, a careful listener might raise an objection. If galaxies beyond a certain distance are receding faster than the speed of light, how can we see them at all? If their light is being carried away from us by the expansion of space, surely that light can never reach us. Surely those galaxies should be invisible. The objection is reasonable, And the answer reveals one of the most counterintuitive features of the expanding universe. The distance at which recession velocity equals the speed of light is called the Hubble radius, or the Hubble sphere. It currently sits at approximately 14 billion light-years. At that distance, the cumulative expansion of space between us and a galaxy produces a recession velocity of exactly the speed of light. Beyond that distance, galaxies are receding superluminally, but the Hubble sphere is not a visibility limit. Many of the galaxies we observe, including virtually all of the galaxies in deep field images, are currently beyond the Hubble sphere, receding from us faster than light. We can see them because their light was not always fighting a losing battle. Consider a photon emitted by a galaxy that was, at the time of emission, well inside the Hubble sphere. The galaxy was receding, but slowly enough that the photon could make progress toward us. The photon began its journey, crossing space in our direction. But during the billions of years that journey took, the universe continued expanding. The galaxy that emitted the photon was carried farther and farther away, eventually crossing the Hubble radius and entering the superluminal recession zone. The galaxy is now receding from us faster than light. But the photon, which left the galaxy long ago, is still traveling toward us. It entered our Hubble sphere during its journey and has been making steady progress ever since. It will eventually arrive at our telescopes, even though the galaxy that emitted it is now receding faster than light and will never be reachable. This is why the observable universe is so much larger than the Hubble sphere. The Hubble sphere tells you which galaxies are currently receding slower than light. The observable universe tells you which galaxies have ever sent light that could reach you. Those are very different questions with very different answers. The Hubble sphere is approximately 14 billion light-years in radius. The observable universe is approximately 46.5 billion light-years in radius. The difference exists because light emitted in the past, when galaxies were closer and receding more slowly, has had enough time to reach us despite the galaxies themselves having since been swept beyond the Hubble distance. But here is the critical distinction that connects the Hubble sphere to the cosmic event horizon discussed later. The observable universe tells you what you can see. The Hubble sphere tells you the current recession speed boundary. Neither of them tells you what you can reach. That answer comes from the cosmic event horizon, which is a different boundary entirely, and it is the one that delivers the truly devastating news about cosmic distance. And this is where one of the most important and unresolved crises in modern cosmology enters the story. The Hubble constant has been measured using two fundamentally different approaches, and the results do not agree. The disagreement is not subtle. It is not within the margin of error. It is a statistically significant discrepancy that has persisted for years, deepened with every new measurement, and resisted every attempt at resolution. Cosmologists call it the Hubble tension, and as of late 2025 it remains the most significant puzzle in observational cosmology. The first approach measures the expansion rate using the early universe. Scientists study the cosmic microwave background and extract from its temperature patterns a detailed model of the universe's contents and geometry. This model, grounded in the lambda CDM framework that has been the standard cosmological model for decades, predicts what the current expansion rate should be. The answer is approximately 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.26 million light-years, space is currently expanding at 67 kilometers per second. The second approach measures the expansion rate using the nearby universe. Astronomers observe Cepheid variable stars to calibrate the distances to galaxies hosting Type 1a supernovae. These supernovae serve as standard candles at greater distances, and by comparing their distances to their measured redshifts, astronomers calculate the local expansion rate directly. This method, led by the SHOES team and refined over many years, consistently produces a higher value, approximately 73 kilometers per second per megaparsec. The difference is roughly 9%. 6 kilometers per second per megaparsec may not sound dramatic, but both measurements are extraordinarily precise, with error bars that do not overlap. The statistical significance of the discrepancy has reached approximately 5 sigma, meaning there is less than a 1 in a million probability that the disagreement is due to random chance. In particle physics, 5 sigma is the threshold for declaring a discovery. In cosmology, 5 sigma is the threshold for declaring a crisis. For years, some researchers hoped the tension would resolve itself as measurement techniques improved. Perhaps the Cepheid distances were contaminated by crowding effects in distant galaxies, where background stars blended with the target Cepheids and skewed brightness measurements. Perhaps dust along the line of sight was dimming the supernovae in ways that were not properly accounted for. Perhaps the early universe models contained subtle assumptions that biased the predicted expansion rate. Then the James Webb Space Telescope weighed in. In 2024 and 2025, the SHOES team used the telescope's superior resolution, roughly 4 times sharper than Hubble's, to re-observe the same Cepheids in the same galaxies. The results matched the Hubble data almost exactly. Crowding was not the culprit. The local measurement of 73 km per second per megaparsec is robust. Whatever is causing the tension, it is not a simple observational error that a better telescope can fix. Meanwhile, the Chicago Carnegie Hubble program pursued an alternative approach using a different type of distance indicator called the tip of the red giant branch method. Early results suggested a middle ground between the two competing values, but updated analyses using James Webb calibrations in 2025 produced results ranging between 69 and 72 km per second per megaparsec, closer to the local Cepheid measurement than to the cosmic microwave background prediction, but not identical. The picture grew more complicated, not simpler. In late 2025, the TD Cosmo collaboration published new results using an entirely independent technique: gravitational lensing of distant quasars. When light from a quasar passes near a massive foreground galaxy, gravity bends the light along multiple paths, creating multiple images of the same quasar that arrive at different times. The time delays between these images depend on the expansion rate. The TDCOSMO results further supported the higher local value, deepening the tension with cosmic microwave background predictions. The crisis is real, the measurements are solid, the disagreement persists, and nobody knows why. Several categories of explanation have been proposed. The most conservative is that some subtle, systematic error remains hidden in one or both measurement methods, despite years of scrutiny. The most exciting is that the tension signals new physics beyond the standard lambda CDM model. Perhaps dark energy is not the simple cosmological constant that lambda CDM assumes. Perhaps its strength has been changing over cosmic time. Perhaps some unknown ingredient in the early universe, sometimes called early dark energy, briefly accelerated expansion just before recombination and shifted the predicted Hubble constant upward. Perhaps the universe contains a population of particles we have not detected yet, such as additional types of neutrinos, that subtly altered the expansion history. This matters for the story of distance in a way that goes beyond academic cosmology. The Hubble constant is not just a number that tells scientists how fast the universe is expanding. It is the conversion factor embedded in every cosmological distance ever calculated. The size of the observable universe depends on it. The co-moving distance to the cosmic microwave background depends on it. The location of the cosmic event horizon, the boundary between what humanity can reach and what is permanently sealed off, depends on it. Every number quoted so far, the 93 billion light-year diameter, the 46.5 billion light-year radius, the 16 billion light-year event horizon, all of them are derived from a cosmological framework that requires a precise value for the Hubble constant. And right now, the two most rigorous methods of measuring it disagree by 9%. 9% may not sound catastrophic, but applied to the cosmic event horizon, 9% shifts the boundary by more than 1 billion light-years. That shift determines how many galaxies fall inside the reachable volume and how many are already lost. The cosmic ruler we have been building is not just broken by expansion and blurred by look-back time. It is also smeared by a fundamental uncertainty in how fast the breaking and blurring are occurring. We are not merely struggling to measure the distance across the universe. We are struggling to agree on the rate at which that distance is growing. Into this debate stepped the dark energy spectroscopic instrument known as DESI. This survey is mapping the three-dimensional distribution of tens of millions of galaxies across vast volumes of space, measuring baryon acoustic oscillations, which are frozen sound waves from the early universe imprinted on the large-scale clustering of matter. These oscillations serve as a standard ruler, a known physical scale that astronomers can observe at various distances and use to reconstruct the expansion history of the universe. In 2024, DESI released its first-year results, and they contained a surprise. When combined with cosmic microwave background data and supernova measurements, the DESI baryon acoustic oscillation data showed hints that dark energy may not be constant. The results favored a model in which dark energy's equation of state evolves over time, deviating from the cosmological constant prediction at a significance of 2.5 to nearly 4 sigma, depending on which supernova dataset was included. In 2025, DESI released second-year results that strengthened these hints. The preference for evolving dark energy persisted, and in some analyses grew more statistically significant. If dark energy is truly evolving, it would be one of the most consequential discoveries in the history of cosmology. A cosmological constant is the simplest possible form of dark energy, a fixed energy density woven into the fabric of space itself, unchanging throughout cosmic history. An evolving dark energy implies that something more complex is at work, perhaps a dynamic field that interacts with space-time in ways the standard model does not capture. This could affect everything: the expansion history of the universe, the formation of structures within it, and crucially, the fate of everything we can observe. But the DESI results are not yet definitive. The significance is tantalizing but not conclusive. Some researchers have questioned whether specific data points in the DCI sample are driving the preference for evolving dark energy, and whether broader or different datasets might dilute the signal. The community is cautious, aware that hints of new physics can evaporate with additional data. More results are expected as DESI continues its 5-year survey, and as the European Space Agency's Euclid mission publishes its primary findings, anticipated in 2026. But even as a hint, the DESI result matters for the story of cosmic distance. If dark energy is evolving, then the expansion history of the universe is more complicated than the standard model assumes. More importantly, evolving dark energy would change the future. A cosmological constant drives acceleration at a fixed rate, producing a predictable long-term future in which the observable universe gradually empties. But a dark energy component that changes in strength could produce a future that is either more or less isolating than the standard prediction. If dark energy strengthens over time, the acceleration worsens and the cosmic event horizon contracts faster, cutting us off from more of the universe sooner. If dark energy weakens, the isolation could slow, buying future civilizations more time to observe the cosmos before the sky goes dark. The nature of dark energy does not merely determine the expansion rate. It determines how much of the universe any future civilization will ever be able to see or reach. What is certain is that the expansion of the universe is accelerating. This was discovered in 1998 when 2 independent teams observed distant Type 1a supernovae and found that they were dimmer than expected, indicating they were farther away than a decelerating universe would predict. The universe was not merely expanding, its expansion was speeding up. Something was pushing space apart faster and faster over time. That something was named dark energy, and it accounts for approximately 68% of the total energy content of the universe. Its nature remains one of the deepest mysteries in physics. Accelerating expansion has a terrifying consequence for cosmic distance. It creates a boundary beyond which the universe becomes permanently inaccessible, not merely difficult to reach, not merely far away, permanently, irrevocably, causally disconnected from us forever. This boundary is the cosmic event horizon. The cosmic event horizon is the maximum moving distance from which light emitted right now will ever reach Earth, no matter how long we wait. It sits at approximately 16 billion light-years. Any galaxy, currently closer than 16 billion light-years in co-moving distance, could, in principle, send a light signal today that would eventually arrive at Earth at some point in the far future. Any galaxy currently farther than 16 billion light-years is already beyond the event horizon. A photon emitted from that galaxy right now, aimed directly at Earth, traveling at the speed of light, will never arrive. Space between us is expanding too fast. The photon will struggle against the current of expansion like a swimmer fighting a river, and the river will win. The photon will be swept backward, carried farther and farther from its target by the growth of space, until it joins the vast ocean of light that will never reach any observer in our region of the cosmos. This is not a temporary condition, it is permanent. As long as dark energy continues to accelerate expansion, the cosmic event horizon will persist, and not only will it persist, it will shrink. As expansion accelerates, more and more galaxies will cross the event horizon, moving from the reachable column to the unreachable column, and none of them will ever return. Now compare the cosmic event horizon to the observable universe. The observable universe has a co-moving radius of approximately 46.5 billion light-years. The cosmic event horizon sits at approximately 16 billion light-years. The reachable universe is dramatically smaller than the observable universe. You can see vastly more than you can ever interact with. Quantify this. The volume of a sphere scales with the cube of its radius. The ratio of the reachable volume to the observable volume is roughly 16 divided by 46.5 cubed. That ratio comes out to approximately 4%. In other words, roughly 96% of the galaxies currently visible in the observable universe are already beyond the cosmic event horizon. We can see them, we can photograph them, we can measure their redshifts and catalogue their properties, but we cannot reach them, we cannot send them a signal, we cannot visit them. No technology that obeys the known laws of physics, no matter how advanced, could ever bridge the gap between us and those galaxies. The expansion of space has placed them behind a causal barrier that is absolute. Some estimates place the unreachable fraction at 94%, depending on precise cosmological parameters and how the event horizon is defined. The exact number matters less than the principle. The overwhelming majority of everything we can see is already gone, visible but untouchable, present in our telescopes but absent from our future. This creates a nested hierarchy of cosmic boundaries that most people have never considered. The entire universe, whatever its full extent, contains within it the observable universe, the sphere of space from which light has reached us. The observable universe contains within it the reachable universe, the sphere from which light emitted now could still someday arrive. And the reachable universe is a small fraction of the observable one. 3 nested regions, each one smaller than the last, each one imposing a different kind of limit on what humanity can know, interact with, or ever experience. The entire universe may be infinite. The observable universe is 93 billion light-years across. The reachable universe is roughly 32 billion light-years across. Your cosmic future, the total volume of space from which any influence could ever touch you, is a tiny bubble within the much larger bubble of what you can see. And that bubble is shrinking. Every second, space continues to expand. Every second, the cosmic event horizon draws fractionally inward in co-moving coordinates as the expansion accelerates. Galaxies that are currently just inside the event horizon will soon cross it. Their light will stretch, redden, dim, and eventually vanish from our instruments entirely. Not because the galaxies have died, but because the space between us has grown beyond the reach of light. Astronomers estimate that approximately 160 billion stars worth of galaxies cross the cosmic event horizon every year. These are not stars that are being destroyed. They are stars that are being disconnected from us, severed from our causal future by the relentless growth of space. Their photons will continue traveling toward us for a while, growing fainter and more redshifted with each passing year, until they become undetectable. But no new photons from those galaxies will ever begin a journey that reaches us. They have, in every meaningful sense, left our universe. This process is already well underway. The most distant galaxies we observe through the James Webb Space Telescope are long past the cosmic event horizon. Their current positions, right now, at this moment in cosmic time, place them far beyond 16 billion light-years. We see them only because their light was emitted billions of years ago, when they were much closer, before the expansion carried them away. The images we capture are the last light that will ever reach us from those regions. We are looking at a farewell that already happened, reading a message whose sender has already vanished over the horizon. What does this actually look like? Imagine tracking a single galaxy as it approaches and crosses the cosmic event horizon. You cannot watch it happen in real time, because the process unfolds across millions and billions of years. But if you could compress that timescale, here is what you would see. At first, the galaxy appears normal, slightly redshifted as all distant galaxies are, but otherwise unremarkable. Its spiral arms are visible. Its star-forming regions glow in ultraviolet and blue light. Its spectrum contains recognizable absorption lines from hydrogen, helium, and heavier elements. It is a galaxy like any other, sitting at a known distance, receding at a known velocity. Then, gradually, the redshift increases. Not because the galaxy has done anything differently, but because the expansion of intervening space is accelerating. The light stretches, blue features shift toward green, then yellow, then red. The galaxy's apparent brightness decreases, not because it is producing less light, but because each arriving photon carries less energy than the one before it. The intervals between arriving photons grow longer. Information from the galaxy arrives more slowly, as though the universe is placing the galaxy on hold. Over cosmological time, the galaxy reddens past the visible spectrum entirely. It fades into infrared, then into microwave wavelengths, then into radio frequencies so long that no practical antenna could detect them. Its image dims below the sensitivity of any conceivable telescope. The galaxy has not been destroyed. It has not exploded or collapsed. It is still out there, still burning with hundreds of billions of stars, still evolving, still hosting whatever worlds and phenomena occupy its disk and halo. But its light can no longer reach you. The last photon that will ever arrive from that galaxy is already in transit, and after it lands on your detector at some moment in the distant future, there will be nothing, no signal, no glow, no whisper of radiation, just silence from a direction where a galaxy used to be. The galaxy has crossed the event horizon, not by moving through space, but by standing still while space grew around it faster than light could compensate. It has been gently, permanently, irrevocably placed beyond the reach of observation, not walled off, not blocked. Simply moved to a distance that light can no longer cross within the remaining lifetime of the universe. This is happening right now to real galaxies in every direction, not hypothetically, not in some far future scenario. Right now, at this moment, galaxies are fading across the cosmic event horizon. Their final photons are in transit, Their farewell is already written in light we have not yet received. This is fundamentally different from any kind of distance human beings have ever encountered. In ordinary life, distance is symmetric. If you can see something, you can reach it. If you can hear someone's voice, you can walk to where they are standing. Distance is an obstacle, but not a permanent one. Given enough time and resources, any gap can be closed. The cosmic event horizon violates this intuition completely. You can see something that you can never reach. You can observe something that is causally disconnected from your entire future. The universe allows you to witness regions of space that are, for all practical purposes, in a different reality, one that overlaps with yours in the past but never in the future. Even the concept of distance itself begins to lose coherence at these scales. What does it mean to say a galaxy is 40 billion light-years away if you can never interact with it? In everyday experience, distance implies a possible journey. 40 miles means you could drive for an hour. 40,000 miles means you could circle the globe. But 40 billion light-years for a galaxy beyond the event horizon does not imply a possible journey of any kind. It is a measurement of something you can observe but never participate in. The number describes a separation that is permanent, growing, and absolute. The distinction between the observable and the reachable universes is the most important boundary in cosmology, and it is almost never discussed outside academic papers. Most popular descriptions of the universe focus on how large the observable universe is. 93 billion light-years across, 2 trillion galaxies, more stars than grains of sand on every beach on Earth. These numbers are staggering, and they serve a valuable purpose in conveying cosmic scale. But they also create an illusion. They imply that all of this belongs to us, that if humanity survives long enough, if technology advances far enough, we could someday explore this vast cosmic territory, mapping galaxies and contacting civilizations and expanding our reach across the observable volume. We cannot. We will never be able to, not because of engineering limitations or lack of imagination, but because of physics. The expansion of space imposes a hard boundary on what any civilization, anywhere in the universe, can ever interact with. That boundary is not at the edge of the observable universe. It is vastly closer, at approximately 16 billion light-years, and it is moving inward. The reachable universe is the true size of the cosmic stage on which humanity's future will play out. Everything beyond it is scenery. Beautiful, ancient, scientifically valuable scenery, but scenery that we can observe only from a distance that will grow forever, lit by ancient photons from a past that belongs to no one. Understanding the cosmic event horizon transforms the meaning of every cosmic distance measurement you have ever encountered. When an astronomer says a galaxy is 10 billion light-years away, the relevant question is no longer how far away it is. The relevant question is whether it is inside or outside the event horizon. Is it part of our causal future, or is it already gone? Is the distance between us a gap that could theoretically be bridged, or is it a permanent severance, a one-way window that allows observation but forbids contact? For most of the galaxies in the observable universe, the answer is already determined. They are gone. We see their past, their present is inaccessible, their future will never intersect with ours. The light they emitted billions of years ago is the only connection we will ever have with them, a connection made of ancient photons carrying information about a moment in cosmic history that ended long before our planet formed. And the situation is getting worse, not slowly, not gradually, but with increasing speed. Dark energy is accelerating the expansion. The rate at which galaxies cross the event horizon is increasing. The fraction of the observable universe that remains reachable is declining year by year, century by century, epoch by epoch. The cosmic landscape visible to future observers will be dramatically emptier than the one we see today. Sit with this for a moment, because the number deserves more than a glance. 94% of the galaxies in the observable universe are already beyond the cosmic event horizon. That is not 94% of some abstract statistical population. It is 94% of everything visible in the Hubble Ultra Deep Field. Those 10,000 galaxies revealed in a patch of sky, smaller than a grain of sand held at arm's length. It is 94% of the 2 trillion galaxies estimated to fill the observable volume. It is 94% of the galaxies whose light has travelled billions of years to reach the mirrors and detectors of every telescope humanity has ever built. Look at any image from a deep field survey. Pick any galaxy at random. The overwhelming probability is that the galaxy you selected is already gone from your causal future. Its present-day self exists in a region of space that no signal from Earth will ever reach. If you sent a message toward it today at the speed of light, the message would travel forever and never arrive. If a civilization in that galaxy sent a message toward you today at the speed of light, the message would travel forever and never arrive. You and that galaxy are connected by a thread of ancient light and by nothing else. The galaxies that remain within the cosmic event horizon, the roughly 6% that are still causally accessible, are not the ones that fill documentary montages or decorate classroom posters. They are the nearest ones, the least dramatic ones, the ones close enough that the expansion of intervening space has not yet overwhelmed the speed of light. The truly spectacular objects, the ancient spirals at cosmic dawn, the gravitational lenses bending light into luminous arcs, the galaxy clusters containing trillions of solar masses, those are the ones we have lost. They are the ones whose light is still arriving, but whose present reality is already sealed behind the event horizon. This is the final cruelty of cosmic distance at universal scale. The objects that teach us the most about the universe, the ones whose ancient light reveals the expansion history, the formation of structure, the properties of dark energy, those are precisely the objects that are farthest away and therefore the first to be lost. The most scientifically valuable regions of the observable universe are the ones most thoroughly separated from us. We learn the most from the places we can never go. What this means for the long-term future of the universe, for the eventual fate of observation itself, and for the deepest question of all, whether the farthest things in the universe are merely distant or whether they belong to a version of reality permanently disconnected from our own, is what comes next. Everything we have discussed so far describes the universe as it exists right now. The observable horizon at 46.5 billion light-years. The cosmic event horizon at roughly 16 billion light-years. The vast gap between what we can see and what we can reach. The approximately 96% of observable galaxies that are already permanently beyond contact. This is the present situation. It gets worse. Dark energy is not merely maintaining the expansion of space, it is accelerating it. The universe is not just growing, it is growing faster with every passing moment. And this acceleration has consequences that will slowly, relentlessly strip the night sky bare. In the standard cosmological model, dark energy behaves as a constant energy density woven into the fabric of space itself. As space expands and creates more volume, the total amount of dark energy increases proportionally because every new cubic meter of space comes preloaded with the same dark energy density as every existing one. Matter, by contrast, dilutes. The same number of galaxies spread across a larger volume means less gravitational pull per unit of space. Gravity weakens as expansion stretches it thin. Dark energy never weakens. It accumulates. This imbalance creates a one-way trajectory. In the early universe, matter was dense enough that gravity dominated. Expansion was decelerating. Galaxy clusters were forming. Structures were growing. Gravity was winning. But roughly 5 billion years ago, the density of matter dropped below the threshold, where it could compete with dark energy's repulsive pressure. Expansion began accelerating. And once that acceleration started, it became self-reinforcing. More expansion means more space. More space means more dark energy. More dark energy means faster expansion. The universe entered a feedback loop that cannot be reversed by any known physical process. The acceleration is subtle by human standards. You cannot feel it. You cannot measure it in a single room or across a single solar system. Gravity within bound structures, galaxies, galaxy clusters, the local group, easily overpowers the expansion. Nothing inside the Milky Way is being torn apart by dark energy. Not yet. But on cosmological scales, the acceleration is relentless, and its effects accumulate across billions of years into something genuinely catastrophic for the connectedness of the universe. Here is what the acceleration does. Every galaxy beyond the local group is receding from us. Most of them are receding faster than the speed of light because the cumulative expansion across billions of light years of intervening space adds up to superluminal recession velocities. As the expansion accelerates, the recession speeds increase. Galaxies that were barely receding fast enough to stay within reach tip over the edge and become unreachable. Galaxies that were receding fast enough to remain visible, their ancient light still arriving despite their unreachability, eventually recede so rapidly that even their light gets stretched beyond detection. They vanish from the observable universe entirely. This is not theoretical. It is happening right now. The rate at which galaxies cross the cosmic event horizon and join the permanently inaccessible volume of space is already staggering, and that rate will grow as the acceleration continues. The event horizon itself is not expanding fast enough to keep up with the objects being swept beyond it. The net result is a universe that is visibly shrinking even as it is physically expanding. The amount of space we can see or influence decreases while the total volume of space increases. We are losing the universe. Slowly, silently, irreversibly. Project this forward. Within roughly 100 billion years, the only galaxies remaining within our observable volume will be the few dozen members of the local group, the Milky Way, Andromeda, Triangulum, and the collection of dwarf satellites gravitationally bound to them. By that point, the Milky Way and Andromeda will have long since merged, forming a single massive elliptical galaxy, sometimes called Mil-Comets-2. The night sky, as seen from a planet in that merged galaxy, will contain stars, millions of them, all belonging to the same local structure. But beyond them, nothing. No distant galaxies glowing against the dark. No filaments of the cosmic web shimmering at the edge of detection. No deep field images teeming with 10,000 galaxies in a pinhole patch of sky. Just darkness stretching in every direction, empty and absolute. Now consider what this means for knowledge itself. A civilization arising in that far future galaxy would have access to extraordinary local information. They could study their own stars, map their own planetary systems, develop physics and chemistry and biology. They could build telescopes and point them outward, but those telescopes would see nothing beyond the gravitational boundary of their own galactic structure. The cosmic microwave background, the ancient afterglow that tells us the universe began in a hot, dense state 13.8 billion years ago, would be redshifted so far beyond the microwave spectrum that no conceivable instrument could detect it. The radiation would still exist, stretched to wavelengths longer than any detector could capture, carrying information so diluted by expansion that it would be physically indistinguishable from absolute silence. Without the cosmic microwave background, there is no direct evidence of the Big Bang. Without distant galaxies, there is no way to discover cosmic expansion. Without expansion, there is no reason to suspect the universe was ever smaller, hotter, or denser than it appears at that moment. The entire framework of modern cosmology, the Big Bang, the expanding universe, dark energy, the age and history of the cosmos, depends on observations that will eventually become impossible. A far future civilization would look out at the universe and see a single galaxy floating in an infinite static void. They might conclude that their galaxy was the entire universe. They would have no evidence to the contrary. Every clue that could tell them otherwise would have been erased by expansion, carried beyond the horizon, redshifted into oblivion. The universe would have hidden its own history. This is not a failure of intelligence or technology. It is a physical limit imposed by the geometry of an accelerating cosmos. The information is not destroyed. It is simply moved beyond reach, placed behind a horizon that no signal can cross, locked away in a region of space-time that has been permanently disconnected from the observer's future. The library still exists. The doors are sealed. We live right now in what cosmologists sometimes call the golden age of observational cosmology. This era will not last. The window through which we can see the large-scale structure of the universe, the expansion history, the cosmic microwave background, the deep-field galaxies, the baryon acoustic oscillation signal, is open today. It will close, not abruptly but gradually, as expansion sweeps the evidence beyond our reach, one galaxy, one signal, one photon at a time. The fact that humans happen to develop cosmology during this window is not something we should take for granted. Much earlier in cosmic history, and the universe would have been too young for the galaxies and structures we depend on to have formed. A few 100 billion years later, and the evidence would have vanished. We exist in a narrow corridor of cosmic time, during which the universe is both old enough to have developed structure and young enough for that structure to remain visible. This corridor is closing. We are watching the universe, while the universe still lets itself be watched. Here is where the deepest unsettling truth of cosmic distance reveals itself. Everything you have learned in this journey points toward a single realization that most people never confront directly. It is not the size of the universe that is terrifying. Size is just a number, and humans are remarkably good at accepting large numbers once they get used to them. 93 billion light-years across, 2 trillion galaxies, 400 billion stars in the Milky Way. These are staggering figures, but they are comprehensible in the abstract. You can write them down, you can compare them, you can rank them. They do not break the way your mind works. What breaks your mind is the realization that the distance across the universe is not a distance at all, not in the way you have always understood that word. Distance, in human experience, is a relationship between two places that exist at the same time and could, in principle, be connected by a path. The distance from your house to the nearest city is a gap you could cross. Both locations exist in the present. A road connects them. The journey is possible. Distance, in this everyday sense, implies accessibility. If you know how far something is, you implicitly assume you could get there, given enough time and resources. Cosmic distance violates every part of this assumption. When you say the observable universe is 93 billion light-years across, you are not describing a gap that could be crossed. You are describing a measurement that combines space, time, and expansion into a single number that conceals more than it reveals. The objects at the far edge of that measurement do not exist in your present. They existed billions of years ago, in a younger, smaller, hotter universe. The versions of them that you observe are fossils. The real objects, whatever they have become in the intervening eons, sit in locations that have been carried far beyond the number you wrote down, swept outward by expansion that continued relentlessly during the light's entire journey. And even if you could somehow travel to where those objects appear to be, you would find nothing there, because the light you followed was emitted from a location that no longer corresponds to any present-day position in the universe. Distance across the universe is not a route, it is a record of loss. Every light-year of cosmic distance represents a year of time you cannot recover, a year during which the source moved farther away, a year during which the information you received grew older and less representative of current reality. The farthest objects in the observable universe are not the most remote places on a cosmic map. They are the oldest moments in cosmic history that light can still deliver to your instruments. Looking at them is not like looking across a vast plain. It is like reading a letter that was written before you were born, by someone who moved to an unknown address while the letter was in transit. And most of those objects are already unreachable. Not unreachable in the sense of being too far for current technology. Unreachable in the absolute sense. Unreachable in the sense that even a signal travelling at the speed of light, launched today and continuing forever, would never arrive at those locations. The expansion of space between here and there is faster than the signal. The gap grows quicker than the message can cross it. The destination recedes permanently beyond the cosmic event horizon, and nothing in the known laws of physics can reverse that recession. Observation is not ownership. This phrase sounds abstract until you grasp what it means in the context of the cosmos. Humanity has observed galaxies whose light travelled for more than 13 billion years to reach our telescopes. We have catalogued them, measured their redshifts, estimated their masses, studied their star formation rates. We have given them designations and filed them in databases. In every practical scientific sense, we have claimed them as part of our observable universe, objects we know about, objects we have interacted with through the medium of light. But we do not own that knowledge the way we own knowledge of nearby objects. The moon is 239,000 miles away, and we can verify that distance today, tomorrow, next year. We can bounce lasers off its surface and confirm it has not moved. The moon is real, present, and accessible. A galaxy at the edge of the observable universe is none of those things. It is real only in the sense that it existed when its light was emitted. It is present only as an image reconstructed from ancient photons. And it is accessible only to observation, never to interaction. We cannot send it a signal, we cannot visit it, we cannot even determine what it looks like right now. The knowledge we have of it is a one-way gift, a message delivered without a return address. Visibility is not access. You can see a galaxy 13 billion light-years away. You can photograph it in exquisite detail. You can publish papers about its properties. But you cannot touch it, reach it, influence it, or receive any future communication from it. It is visible the way a memory is visible, a thing that once was, preserved in a medium that travelled forward in time, while the original continued on a path you can never follow. This distinction between what you can see and what you can reach is the central horror of cosmic distance. It is not the bigness that undoes you. It is the disconnection. The universe is not merely large. It is fractured. It is partitioned into regions that can observe each other's pasts but can never share a present. The cosmic event horizon draws a permanent boundary between the part of the universe you could theoretically interact with and the part that is forever sealed off. And that boundary is not a wall you might someday break through with better technology. It is a consequence of the expansion of space itself, written into the geometry of the cosmos as deeply as gravity or the speed of light. The farthest things in the universe are not just distant, they belong to a different causal reality. Their future and your future will never intersect. No event that occurs in your region of space will ever influence them. No event that occurs in their region will ever influence you. You are separated not merely by trillions of miles, but by the structure of space-time itself, which has expanded between you so thoroughly that the two regions are, for all physical purposes, different universes wearing the same name. This is why the distance across the universe is worse than you think. You expected a very large number. You expected to hear that the universe is incomprehensibly vast, that the distances between galaxies beggar imagination, that the scale of everything dwarfs human experience. And all of that is true. But the real revelation is not the size, it is the nature of the distance itself. Cosmic distance is not a measurement of how far something is. It is a measurement of how separated you are from it, in time, in causal connection, in shared reality. A galaxy at the edge of the observable universe is not far away the way another country is far away. It is far away the way yesterday is far away. You can see evidence that it existed. You cannot visit it. You cannot change it. You cannot interact with it. It has moved on without you, carried by the expansion of space into a future that will never overlap with yours. The simple idea that you could someday measure the distance across the universe and call it a single number, a cosmic ruler stretching from here to the farthest thing, collapses under its own assumptions. There is no single distance across the universe. There is the light travel distance, the comoving distance, the look-back time, the angular diameter distance, and each one tells a different story about the relationship between you and a distant object. None of them describes a route. None of them promises accessibility. They are measurements of a separation that is growing, deepening, and hardening with every passing second as dark energy drives the expansion faster. We can observe ancient light. We can measure vast structures. We can map galaxies and infer horizons. But observation is not ownership. Visibility is not access. The universe can show us places whose present reality is forever separated from ours. It can display the childhood portraits of galaxies that have since grown old in regions we will never witness. It can deliver photons from events that occurred before our planet existed, carried to us by a cosmos that has been expanding behind them the entire time, quietly and permanently widening the gap between the message and the sender. The distance across the universe is not simply an enormous number of light years. It is a boundary drawn in time, expansion, and causality. It tells us that the cosmos is not a single shared space that humanity could someday traverse. It is a patchwork of causally disconnected regions, each one visible to the others only through the ancient light that escaped before the expansion sealed them apart. We live on one patch. We can see the fading edges of countless others, and the space between us and them is not a bridge waiting to be crossed. It is a severance that has already occurred, silent and total, written into the deepest architecture of reality. The farthest things in the universe are not just far away. They are gone, not destroyed, not vanished, simply moved beyond the reach of any signal, any journey, any future connection. They exist in a present we will never observe, in a location we will never determine, in a version of reality that shares our origin but no longer shares our fate. They were part of our universe once, in the earliest moments, when everything was close enough for light to connect it, but expansion separated us. Time deepened the divide, and now they belong to a cosmos we can remember but never revisit. The distance across the universe is worse than you think, because it is not really distance at all. It is loss. It is the quiet, permanent, accelerating dissolution of the connections between everything the universe once held together. And no telescope, no spacecraft, no theory, and no future technology can undo what expansion has already done. The universe showed us everything it could, and then it took most of it back.